Now, let's move to the example 23.8. Okay. In this example, they want to calculate the electric field from the uniformly charged distribution on a disk. Now we have the disk, not the ring, at point P along the axis of the disk, along the axis of the disk. Point P here, and we want to know what is the electric field. To calculate the electric field in this case, in general we can do the same thing that we divided the charge Q on this plate. Okay, to be the very small pieces, a large number of very small pieces, and assume that each piece is a point charge and calculate the dE at this point. Anyway, that is not a good idea. It is because we have the better method to do that. To divide the charge distribution into the small pieces is not the only way that we divide it into the point charge. We can divide the charge distribution like this into any shape that we know how to calculate the electric field from that part. In this case, you can see that this is a circular disk. The better way to divide this into the small part is that we divide this circular disk as the set of the circular ring. Okay, it means that we divide from the small ring at the center and increase the radius of the ring until we reach the limb of the disk. Okay, and why this is a better idea? Because we know from the previous example that if we look on a particular ring, we already have the expression for the electric field from each ring. From the previous example, we know exactly what is the electric field from each ring. It means that we can calculate the dE. We can calculate the dE from each ring. And from the previous example, we know that the dE will point along the axis of the ring, which is also the axis of the disk. Okay, so we can calculate the electric field from this ring, and then we sum up for our ring. The difference of each ring is the radius arm. Okay, they use a small arm here. Okay, the difference of each ring is the radius arm. It means that if you look at the inner ring, the R is small. If you look at the outer ring, the R is large. So the value of dE here is a function of R. Okay? And what we have to do is that we sum up the electric field from each ring. We know that for each ring, the direction of dE are the same. It will point along the axis of the disk. So we don't have to worry about the direction of DE. What we have to do is to sum up the magnitude of the DE of each ring, and we will get the solution. So we have that E is equal, you can see that now I will look only at the magnitude of E. So E is the integral of dE for all ring. Okay, for all ring. But from the previous example, dE is equal dE is equal to kx if x is a distance from the center of the disk to point P, okay, time in this case it will be r squared plus x squared to the power of 3 over 2. Okay. In the previous example, this is the position of A, that is the radius of one ring. But now we use R as a symbol of the radius of each ring, and R is a variable. So here we use R. This is the dE for this ring only, and we do the integration. It means we sum up for all rings. So R is different for each ring. So in this integration, R is a variable of integration. Okay, and we have to time here we call it the dQ. dQ here is the charge on each ring, and we assume that we have a very thin ring here. We divided this to be the large number of very thin ring. Okay, so it means that the amount of charge on each ring is quite small. So we do the symbol dQ like this. Okay. So to do the calculation, we have to perform the calculation for this integration. But now you can see that we have two variables R and dQ. X is a constant again, so we can move this kx out of the integration. We will do that soon. To do this calculation, we have to write down dQ in terms of R, which is not hard to do that. If we say that the thickness of each ring, here, the thickness of each ring is dr. Okay, so it means that the area of each ring is dA equal to 2 pi r dr. Okay, we can use this expression just because this is the area of the very thin ring. If you have the thick ring, you cannot use this expression. But to use this expression, you can use that for the thin ring only. 2 pi r is the circumference of each ring, and dr is the thickness of each ring. So we have the dA equal to 2 pi r dr. Now, what is the value of dQ? In this problem, we assume the uniformly distribution of the charge on the disk. So we can define the area charge density sigma is equal to the Q over A, where A is the area of the ring. So we have that sigma is equal to the Q over pi. They use the symbol big R squared. Okay. Here, big R is a radius of the disk. So from this definition of the area charge density, we can write dq as a sigma dA, right? Sigma is a charge per unit area, Q over A. But we want to know the charge on this small area only. So we multiply the charge per unit area with the area of this ring. So we have the charge on this ring. So dq is equal to sigma dA, which we can expand this to be sigma times 2 pi r dr. Okay. Now we can express dq in terms of r and dr. So we substitute this into this equation. We have that this equal to integral of all ring of kx over r squared plus x squared to the power of 3 over 2 of sigma 2 pi r dr. Okay. Since the charge is uniformly distributed, it means that sigma is a constant in this case. This is true only when the charge is uniformly distributed. Okay. If the charge is not uniformly distributed, you cannot assume that sigma is a constant. But in this case, we assume that the charge is uniformly distributed, so the sigma is a constant. So we have this. It means that we can take these terms out of the integration because they are all constant. So we have that this is the integral of all ring of kx 2 pi 2 pi sigma kx integral of r dr over r squared plus x squared over 3 over 2. Okay, that is a mathematical expression to do the integral here. So what left is the calculus technique, okay, which we can use the method of the changing of the variable. Here we can see that from the calculus we have that r dr is equal to the half of dr squared. Okay, so we can put this r dr here, and we have that is equal to the dr squared over r squared plus x squared over to the power of 3 over 2. I'm sorry. It's equal to the integral of dr squared over r squared plus x squared to the power of 3 over 2. And in front of this we have pi sigma kx. The number 2 here cancel with this half. Okay, and when you put this RDR to be equal to half of dr square here, it will cancel with this 2. So the factor 2 here disappear. Now you can see that we have the same variable in our integration. I will not do the detailed calculation here. You can follow the example 23.8 in the book. To get the final solution, that E is equal to the 2 pi k sigma. The number 2 here come back again because of the process of the integration here, and time 1 minus x over big R square plus x square to the power of 3 over 2. I'm sorry, to the square root to the power of half or the square root of that term. Okay, that is the solution. I will give you as a do it yourself to perform the integration here to get this solution. So this is a solution for this problem of the charge distribute uniformly distribute on the disk.